Hey everybody, this is Professor Ross here to talk about fraction comparison and fraction equivalence. Let's start by talking about fraction comparison. One of the things we want our students to be able to do is to compare two fractions, like compare 1/4 to 3/4, and to be able to say which of those is bigger and which is smaller. Now, you might look at that and say, that's really easy, Professor Ross. 1/4 is clearly smaller than 3/4. However, if we're not careful, we may find scenarios where that's not exactly true. For example, let's say you decide to go to the pizza parlor with your friend, and you order a super extra large jumbo size pizza, and your friend orders a little personal pan pizza. And you eat 1/4 of your super extra large jumbo size pizza, and your friend eats 3/4 of their personal pan pizza. Clearly, the amount of pizza you ate, your 1/4, was bigger than the amount of pizza your friend ate, their 3/4. So, am I trying to bring this up just to make everything all confused and a jumbled mess? No. What I want to show is that it's important, as always with fractions, to understand what the whole is. If we're trying to compare fractions and we're not using the same size whole, if we have two different size wholes, our fraction comparison is in some sense meaningless. We have to go to some other way to compare them. So one of the underlying assumptions with fraction comparison and fraction equivalence is that we're always comparing the same size wholes. And then once we're on the same page with that, we both have the same size wholes, then problems like this, 1/4 compared to 3/4, are actually pretty easy for many students, especially when they understand what the denominator means. We've taken our whole and we've cut it into 4 equal pieces. And what our numerator means, that 1/4 means we've got one of those equal sized pieces, and 3/4 means we've got 3 of those equal sized pieces. And you can see when we've got the same size wholes and the same size pieces, we really end up just comparing 1 to 3. And 1 is smaller than 3, so 1/4 is smaller than 3/4. It's not a very hard thing for students to figure out how these work, especially when they're comfortable with what the numerator and denominator means. And when they've done things like fraction iteration, counted out 3/4, they know that's going to be more than 1/4. A little bit more challenging for students is our comparisons where we have the same denominator. Like here I've got unit fractions, they're both just one piece, but the denominator is different. Same numerator, different denominators. So students are often tempted to look at these two numbers and to think, oh yeah, 4 is smaller than 6, and so 1/4 must be smaller than 1/6. It's a really, really tempting thing to think, but it's actually not accurate. And once again, we got to point students back towards what does 1/4 mean? Well, it means I've taken a whole and cut it into 4 equal sized pieces, and I've got one of them, whereas 1/6 means I've taken a whole and I've cut it into 6 equal sized pieces, and I've only got one of those. And so since I've got 6 pieces here and only 6 pieces over here, only 4 over here, this is clearly the smaller amount, and so 1/6 is smaller than 1/4. These are great fraction comparison problems to be doing with your students, a lot of, just to get them comfortable with the idea that as the denominator gets bigger, we cut the whole into smaller size pieces, and so we get a smaller amount. That lays some pretty good groundwork for some of the most challenging fraction comparison problems where we have both different numerators and different denominators. So the size pieces cut are different, and also the number of pieces we have are different. These can be challenging for students. There are certainly some procedures we can use, but we also want to give students a chance to think about what the meaning is and how they can do some reasoning without necessarily relying just on a rote procedure. So for example, how could I compare 2/3 to 7/10? Well, we saw pictures have been helpful so far, so let's try some pictures. There are cases like this where the pictures look very, very similar to each other. It's kind of hard to say definitively if 2/3 is bigger or less than 7/10, or maybe the same as, just by looking at the picture, because they look so similar. So pictures, while they can often, like in a scenario like this, help us get a great sense of what's going on, sometimes they don't help us come to a definitive answer. What else could we do? We could think about things like benchmarks. Use a benchmark of a 1/2, and what a 1/2 means, like, okay, if I was going to have a half of this whole, it would look like this, and how much more than a half do I have here? Compared to if I have a half here, how much more of a half do I than a half do I have here? So using benchmarks can be a helpful tool as well. Another great way to do some reasoning here is to think about how much is missing. So instead of focusing on how much we have, think about how much is missing. I'm missing a third here. Here I'm missing 3/10. Is there a good way for me to compare 1/3 to 3/10? And sometimes that's a real helpful approach. So there's some different kinds of reasonings that we can do, but ultimately what comes in really handy and what we want to try to steer students toward is realizing that if we get these wholes cut into the same size pieces, then the comparison becomes like this first one, and it's essentially trivial. We just look at the number of pieces in each. So the idea of a common denominator, which is probably some language you've heard lots throughout your math career, but this idea comes in really important in fraction comparison. We're going to see it's important in fraction equivalence, and then it's also important in some fraction operations. So what's a common denominator? Denominator means the size of pieces, and so we want to try and get the size of pieces in common. For example, here we could say, okay, let's cut both of these wholes into 30 pieces. Now that's going to be kind of hard to draw. I would need to split each of these into 10 pieces and 10 pieces. So this one's kind of a tough one to draw. I'd have to cut these into 3 pieces each. But if I could do that, I could figure out how many of 30ths I have, and then it's simply a matter of recognizing that this one has 21 30ths, while this one only has 20 30ths, and then I know, oh, this one's bigger because it has 21 30ths. So this idea of common denominator becomes a key foundation for a lot of stuff we're going to do with fractions. And so it's an important idea to start planting in students' minds, or if students come up with that idea, it's a real big one to highlight and applaud when students think about getting the same size pieces. Let's talk about fraction equivalence. So we've talked about comparing larger and smaller ones. What happens when two fractions are the exact same size, like 3/4 is the same size as 6/8? How do I know that? That's a really important question for students to understand. How do we know when two fractions are actually equal? And you may have learned something like a little procedure in school where you said, oh, well, I can do 3 times 2 equals 6, and 4 times 2 equals 8, and that means those two fractions are the same. And while that is true, and we can do some mathematics to prove that, it doesn't explain why we know they are the same. It's a procedure. Multiply that by 2 and that by 2, and it gives us something. But if you can't explain why that procedure works, in some sense it's not a very useful thing, because it's very easy to confuse that procedure and say, well, maybe I could do this. 3 plus 2 and 4 plus 2, and 3/4 equals 5/6. And all of you say, no, that's not right. You can only multiply or divide. Well, why? We want to try to understand why 3 times 2 and 4 times 2 gives us an equivalent fraction, whereas adding or subtracting doesn't. First of all, let's just think about a picture here. What is 3/4? Okay, that means I've taken my whole and split it into 4 parts, and I've got 3 of those. What is 6/8? That means I've taken my whole and I've split it into 8 parts, and I have 6 of those. Now, is this little drawing enough for us to be totally convinced that these two things are equal? They sure look pretty much alike, but we found, talking about fraction equivalence, that just pictures just looking alike isn't always necessarily a guarantee that that must be true. So what can we do, what can we reason here that helps us understand why these two are equal and what this times 2 thing has to do with anything? Let's think about what it means when we do 4 times 2 and we get 8. 4 times 2 giving us 8, that means that these 4 pieces down here, I'm taking each of the 4 pieces and I'm multiplying it by 2. In other words, I'm taking my 4 pieces and I'm splitting them each into 2 pieces. What does that end up giving me? 8 pieces. 1, 2, 3, 4, 5, 6, 7, 8 equal sized pieces. So when I multiply a denominator by a number, I am what we call partitioning my whole into more pieces. 4 times 2 is 8, means I've taken my fourths and I've split them each in 2 parts and I've got 8 parts. Why should I also do 3 times 2? Look at our picture. Here were our 3 pieces, 1, 2, and 3. What did I do to each of those 3 pieces? I split them into 2 equal parts because I was taking all my pieces and splitting them into 2 equal parts. When I have 3 things and I split them into 2 each, I end up with 1, 2, 3, 4, 5, 6 things. So what we're actually doing when we do that multiplying is we're partitioning our bigger pieces into smaller pieces, and our corresponding ones we're interested get partitioned as well, and we end up with the exact same thing we see over here, 6 of our 8 equal sized pieces shaded in. So that's what this whole times 2 thing is all about. You may also remember from something like a high school algebra course saying something along the lines of, well, 3/4 is really times 2 over 2, and 2 over 2 is really the same as 1, and so I'm really just multiplying by 1, and anything times 1 is the same as itself. That certainly is a valid argument. It's probably something that that students, when they're dealing with fraction equivalence in 3rd, 4th, 5th grade, would not really make as much sense of as this idea of partitioning. So I like to focus on the idea of partitioning rather than memorizing some rule about multiplying by 1. How about the other way around? You've probably seen this kind of thing. You can divide 6 by 2 and, sorry, that's a weird looking 2. Here we go. So divide 6 by 2, divide 8 by 2, and 6 divided by 2 is 3, and 8 divided by 2 is 4. What is that about when I'm dividing by 2? Now I'm taking 6/8, and if I do 8 divided by 2, I'm actually putting together into groups of 2 like this, and like this, and like this, and like this. I like to use the term chunking. I take my 8 pieces and I chunk them together into groups of 2, and how many pieces do I end up with? 4 pieces. That's exactly what the denominator is saying. I'm saying I took my 8 pieces, put them together by 2's, and I ended up with 4 pieces. Why do I do 6 divided by 2? Because I had 6 shaded in things, and I put them in groups of 2 each, and I ended up with 3 that were shaded in. 1, 2, 3. And so this idea of dividing by the same thing is this idea of chunking things together to also give us equivalent ratios. One thing I want to mention, some old terminology used to say something like 6/8 is reduced to 3/4. But we really want to avoid using the word reduced because it leads students to believe somehow 3/4 is smaller than 6/8. So we avoid the word reduced. We can use the word simplified as a better term to use. All right, so we've got some key ideas here about fraction comparison and fraction equivalence. We want to work with students to build understanding in meaningful ways as they compare and create equivalent fractions.